Okay, we're leading right up to Brian of that parallel. How does it work out here? Let's talk about conductor ampacity. Okay, this is Article 100. It's the maximum current in amperes that a conductor can carry continuously under the condition of use without exceeding its temperature rating. So here's the philosophy. Well, let's go to this to a table here. If you go to the code book, and actually we'll go to the code book itself because that way it's more powerful. I searched for 310.16. Apparently we have already reviewed this, that this table, ampacity, is based upon not more than 3 current carrying conductors at an ambient temperature 30 degrees C. And that is what the code says. That is the condition. The wires listed on table 310.15b16 can carry its rating continuously under the condition of use. If you have no more than 3 current carrying conductors and the ambient temperature is about not more than 86 degrees Fahrenheit, then let's go to something crazy. Let's go to 14 gauge wire. What is the ampacity of 14 gauge wire? It is 25 amps. Everybody agree with that?
Yes, sir.
That means I can put how many amps on a 14 gauge wire according to the ampacity requirements and according to the condition no more than 3 conductors in a raceway at an ambient temperature 86 degrees Fahrenheit. I can have how many amps on that conductor continuously?
25.
25. And if you do that, the maximum current 25 that a conductor can carry on the condition is without exceeding its temperature. If I put 25 amps on a 14 gauge wire continuously, it's going to achieve what temperature?
90 degrees Celsius.
90 degrees C, which is fine. The wire's rated 90 degrees C. It's rated to carry 25 amps continuously. It's fine. Now, we did cover something in 210.19. We covered something in 215.2 that when you size the conductor to a piece of equipment, Eric, right? If I'm terminating on equipment, forget about the ampacity. Just simply, you have to size the wire to the terminal rating. Now, look at this table here. If 90 degrees C, you can see, gives me much higher amperes. Let's take a perfect example, 8 gauge wire. Well, you go between 40, 50, and 55. So the wire can carry 55 amps continuously. But if I'm terminating this on a circuit breaker that's rated 100 amps or less, 110.14C1A says I have to size the wire to the terminal rating, and the terminal rating of 100 amps or less is 60 degrees C. That means that that wire is only rated 40 amps on that terminal. And if I needed a 50 amp circuit breaker and a 50 amp receptacle, I could not use 8 gauge wire. I would have to go to a 6 gauge wire at 60 degrees C. But 110.14C1A, like 2, says, well, you know, or 3, it says that, well, if you can get the terminals to be rated 75 degrees C, well, then you could size the wire to the 75 degrees C, and if you have a 50 amp breaker and a 50 amp receptacle, you could then use an 8 gauge wire. Are we in agreement with that? So the terminals determine the size. But if I ask you a question in a code, I give you a multiple choice question. This is an exam prep. What is the ampacity of 8 THHN? Let's look at the table. 8 THHN is rated what?
55
amps. What's the ampacity of 12 THHN? 30. Now, if I ask a different question saying, what is the maximum overcurrent protection you can have on a 14 gauge wire? 15. 12 gauge wire, 20. 10 gauge wire, 30. Except as permitted in E and G. So that was 240.4D, because, see, if we take a look at the double asterisk here, it takes us down to the bottom, and it says you need to refer to 240.4D, and 240.4D says except as permitted in E through G, and G had the rules on motors and air conditioning. So if it's not a motor load, it's not an air conditioning load, it's 14 gauge wire, 15 amps, 12 gauge wire, 20 amps, 10 gauge wire, 30 amps. That's the rule on overcurrent protection. But it doesn't change the ampacity. If I tell you, listen, I have a 100 amp load, and I have a 100 amp breaker and let's go with a 125 amp breaker. What size wire do I need? Well, since it's over 100 amperes, we go to 310/15. I'm sorry, we go to 110/14C1B over 100 amperes. It says you size the conductors at what rating?
75.
75. So 125. I now not use the 60. I'm going to go to the 75. I need a 125 amp breaker. Then, well, it all depends on the load. Is that right? We had 240.4B. That says where if it doesn't correspond to the standard size, well, then you could take a 115 amp wire and put it on a 125 amp breaker, assuming it can take care of the load. So that answer then would be a 2-gauge wire. Are we okay with just that? Okay, so now let's just go back to our rule. We know what the ampacity is. It's under the condition of use. We come to this graphic here saying that the table itself is based upon an ambient temperature, 86 degrees Fahrenheit, and no more than 3 current carrying conductors. Now, there is something that we're going to call ampacity correction. That's when you're bundling an ambient temperature. So if the temperature, somehow we'd like to make this look like a temperature, if we can make, if the temperature is above 86 degrees Fahrenheit or below 78 degrees Fahrenheit, then the ampacities that was listed on the table that we just looked at will be different, because the table is based upon 3 wires at a certain temperature. Well, if you change the temperature, then change the ampacity. Now that's called a correction. If you bundle more than 3 current carrying conductor raceway, we have what? Black, red, blue. There's your parallel, Brian, that we were looking at, right? There's your 2 parallel.
No.
Okay. If you have more than 3 current carrying conductors, then you have to adjust the ampacity according to table 310.15B3A. And this is called ampacity adjustment. So let me just review what I'm saying here. The ampacity is its current carrying ability to carry current continuously under a condition of use. When you go to the table, 3 wires, 86 degrees Fahrenheit. If the temperature is elevated above 86 degrees Fahrenheit or below 76 degrees Fahrenheit, then we have to correct the ampacity on the table. If the number of conductors is more than 3, then we have to adjust it. Years ago, we said we had to do what with the wire?
Derate.
We had to derate the wire. But we don't call it derate anymore. You're going to correct it. It's temperature. You're going to adjust it because of bundling. You with me? So you'll see the code will be very consistent about that. Where the ampacity of the conductor has been adjusted or been corrected or adjusted. That's what they're talking about. Now let's go on. This is the ampacities under the condition of use that we talked about that. Brian, I think we need to put double asterisks here and then put a double asterisk on the bottom of that table. And that's in our book. Now, here's a basic rule. It says, look, where there's more than one ampacity rating, where more than one ampacity rating applies to a single conductor length, you will use the lower ampacity for the entire circuit. In this case here, we have conductors on a roof. Without getting into too much detail, let's just say that this correction is 0.58. We don't even know what this is. All I'm just saying is that this wire is rated 17.4 amps, okay? Now, we started with the ampacity because, where's the 12 gauge? Okay, 12 gauge wire is rated 30 amps. Let's go back to the page here. 12 gauge wire is rated 30 amps, okay? But because it's elevated on the roof, because we had an adjustment, we had a correction, that wire is 17.4. The fact the wire on the side here has no solar exposure, it's not on the roof, this wire on the side here is 30 amps. But the wire on the roof is going to be 17.4. And what this rule says, that you always use the lower ampacity whenever there's going to be a difference in ampacities on a particular conductor length. Are we good with that? Then there's an exception. The exception says, well, wait a minute now, hold on a second. Yeah, you have these wires that's on the roof here. And yes, it is a 0.58 correction factor. And yes, this wire is rated 17.4. But if the length of the wires, let's read it, where different ampacities apply to part of a circuit, the higher ampacity can apply to the entire circuit if the length of the corrected or adjusted ampacity does not exceed 10 feet the lesser of 10 feet or 10% of the length of the total circuit. So we have to measure this, right? If this does not, let's say this happens to be, I don't know, these panels are probably not the scale, so we probably need to make these solar panels a little bigger. Brian, you'll get with Mike on that to kind of get a scale there. Okay. Let's just to say that this, well, this is probably not even right then. Let's say with Mike, we move this over a little further, and this is, gosh, this can't be how many more feet than the whole length here?
Oh, there ain't no
10
there ain't no 10 foot up there.
No, I know that, but what I'm saying is that, but it can't be more than 10% of the length of the total circuit.
Right.
So if this is, let's say, 20 feet, right, and this is 2 feet, well, that 17.4 amp wire we can ignore because it's not more than 10% of the entire circuit length. So if this was 20 feet total length, then 2 feet up here does not exceed 10%, then we're okay. You follow me? So where you have an adjustment or a correction. Now watch this, Eric. I'm going into a building, and I'm looking at the panel. David, especially you. I'm going into this residential building, and I'm looking at all these Romex. They cable tied all these. They just brought them all together. They just bundled the whole thing. You're like, whoa, what are you doing? You can't bundle all those conductors. Yes, I can. I can bundle the conductors, assuming that each of the home runs are 50 feet. Right? Let's say these are all home runs, and they're 50 feet. Then I can bundle them up to how many feet without having to worry about capacity adjustment?
Well, 2 feet.
No.
5 feet.
I'm trying to get us to the exception. We always been
Okay,
thinking about that
50
2-foot
feet.
rule.
Yeah,
And you're right about the 2-foot rule.
yeah.
But there's another rule that says, look, if the length of the conductors do not exceed 10% of the entire length of the circuit, maximum 10 feet, then you go with a lower ampacity. I mean, you go with a higher ampacity. But I would rather work a little bit step further. I'm not going to figure out the lower ampacity because I'm going with a higher ampacity. But I only do the lower ampacity when I can't use the higher ampacity. So if I look at something and I see 5 feet of Romex all bundled inside there, I don't even worry about it because it didn't exceed 10% of the length of the entire circuit. Didn't exceed 10 feet. So we really have a 10-foot rule for 100-foot circuits, a 9-foot rule for a 90-foot circuit, a 7-foot rule for 70-foot circuits, a 5-foot rule for 50-foot circuits, a 3-foot rule for 30-foot circuits. You with me?
When did that exception come in?
That has
Oh,
been
it's been there
there. I
forever.
remember finding this probably in the late 1980s. But it's a code change, which allows us to review it and discuss it. So I don't know how far it actually has been in there. Michael?
This is one all of our contractors should mark in their book. Know where this trump card is.
Exactly
It can
right.
save you a lot of trouble.
Every single time an inspector says to you, you're bundling those cables and you have to use an adjustment, the answer is, okay, I'll adjust it. It will be lower than what I'm having. I will then use the exception. I'll go up to 10 feet and then we'll go the higher one. Or we can save each other a lot of time. It's not more than, it's going to be less than 10 feet. Okay, it's less than 10% of the circuit. I don't even do the calculation. I don't waste my time. So I can bundle everything I want to as long as I don't exceed the 10% rule.
Another one that gets you there also is the 244B rule, next size breaker. Even if you do your calculations, you're calculating from the 90-degree chart. Your breaker is still in range. So there's multiple ways right there where you've bundled to get by it, but this is the trump card. I don't have to calculate nothing. We're done.
We don't calculate it.
Yeah.
An M cable is 90C anyways.
Right.
So you can use a 90C column anyways.
Right. But we don't
For
worry
your-
about calculating it because,
That's it.
I'm only bundling a couple of spots here.
Right.
Now, okay? Good here? All right, move on. But I wanted to cover that one. Okay. Ampacity temperature correction. Now, let's talk about correction. 310.15b2a. Now, if it's between 78 and 86 degrees Fahrenheit, okay, let me go to another table here. Here's your correction. Let's just go with Fahrenheit right here. There's no correction between 78 and 86 degrees Fahrenheit. So 78, 86. So really, if we go to the code book table, this right here should say, based on an ambient temperature of what? 78 to 86 degrees, because that's the range that this value is working from. Now, if you happen to make it warmer than 86, 87 to 95, that's the next block. That says that you correct it based upon 90 degrees C. Brian, let's remove the 75 degrees C correction, because we would never have a correction to 75 degrees C in today's world. I would then correct it with a multiplier of 0.96 if it was warmer. And zero, by the way, between 87 and 95, probably, I think it would take every application there is. I don't know, there might be a place, an ambient temperature could be higher than 95 degrees C, and we could look it up and we can find out, but it's not likely. So higher the temperature, you have the multiplier, and if you had the lower the temperature, let's say you got a little cooler, little refrigeration equipment area, or whatever the case may be, well, then you have a different multiplier. Eric.
Yeah, it's good to be aware to make sure your company doesn't have policies that also affect this. I worked for a company on the Gulf Coast that they said we want everything to be put in for 40-degree ambient, so for cable longevity and stuff like that. So it doesn't really matter. The actual ambient may be 30, but if your company says design it for 40, well, that's what you do.
Yeah, well, you do. Here is the table. You're saying if somebody says we want you to figure it at 40 degrees C ambient,
Right.
and that is between 96 and 104.
Right. The interesting thing about that is that if you use 90-degree insulation, and if you look at the 31015B16 and multiply the 90-degree column, every number by 0.91, in every single case, you get a number that's slightly above the 75-degree column.
You know, I wanted to actually do that. I was thinking, I'd like to take the 75 degree C column, okay? And I'd like to find out what is the multiplier. Is it consistent on every single one to get me the 90 degree C? And what is that multiplier?
Yeah,
and I haven't done it.
So it effectively means that everything's 40-degree ambient.
Okay,
as
you're
long
saying
as you
you've
use-
done that. When you use 90 degree C wire,
Right.
and you go to the multiplier, you say, listen, 0.91 would be the one that would work with me, that would get me
Right.
down to the 75 degrees C. So then all I have to do is say, okay, up to 40 degrees C or up to 104 degrees Fahrenheit, I don't worry about it all, because when I take the 90 degrees C and I adjust it down by the temperature correction, it gets me back down to the ampacity that's fine for the 75 degrees C, and I had to size it for the 75 degrees C.
Exactly.
So what I'm trying to do is we're trying to just solve some problems. And that is like, okay, if it's 104 degrees Fahrenheit or less, has no effect. If you're bundling conductors, not more than, if the change in the ampacity is not more than 10 feet, okay, then it has no effect. Then we can just reduce our stress level. Okay, let's go back over here. All right, so now let's go to a calculation. 78 to 86, multiplier 1, the ampacity of 12 gauge wire rated 30 amps is 30 amps. You make it a little cooler, the correction factor is 105, and that comes out to be 31.5 amps. Ampacity is higher. If it's higher temperature, 87 to 95, correction factor is 0.94, comes out to be 28.2 amps, a little lower ampere, but considerably less, whatever. Okay, here's your temperature correction we talked about. Now, we're going to go now to conductor ampacity adjustment. And we're leading up to, Brian, the scenario you brought up, where 4 or more current carrying conductors are in a race where a cable are bundled for a length of longer than 24 inches. The ampacity conductor must be adjusted in accordance with 310.15b(3a). I'm not quite sure. I have to think about this longer than 24 inch rule, because I know that I might go up to 10 feet. So I think what I like to do is just simply say, whenever you're bundling the conductors, you have to, no, because if it's 24 inches or less, let's take a look at that rule. Let's see how they use that language in there. It's up here. So the adjustment factor does not apply to conductors in a raceway having a length not to exceed 24 inches. With me? So back over to our graphic. If it's a raceway not to exceed 24 inches, all right. Do me a favor, Mike Colbert. Let's just make this simple. When you bundle 4 more conductors, you have to adjust the ampacity just to get that started. And then we can then have the exception and say, well, it doesn't apply here. So here's the adjustment. And our example here was, okay, we have here what? 2, 4, 6 conductors. 6 conductors, it's going to be an 80% adjustment factor. Now, why are we doing this? And Brian, leading up to your scenario there, and we might change the color of these conductors. Actually, we are going to change the color of the conductors. If you have 3 conductors in a raceway, the heat on those conductors have a certain amount of surface area that's going to allow us to radiate that heat. Okay? So therefore, 3 or fewer conductors, no ampacity adjustment. I want to change these to black, red, blue, because I really don't want the neutral conductor in this example, because the neutral conductor generally is not a current carrying conductor. So if I had 8 conductors, well, let's say we had, in your case would be what, 6?
6.
What if we had the 2 neutral conductors, black, red, blue? We had 2 neutral conductors. Okay, forgetting about the neutral conductors, see the problem is and we're paralleling, it's because it's just physically, they can't dissipate the heat.
I guess where I always struggle is, and let's just assume, let's make it simple, it's 1,000 watts going through the wires. Well, if there's 1,000 going through 3 or the same 1,000 going through 6, I don't understand how it can make more heat.
Here's the reason why. You're absolutely right. The heat is going to be the same. Here's your 3 600 kc mills, okay?
Right, yes.
And here is your 2 parallel sets of 3/0. So Mike Colbert, make sure we make it to exact scale between 600 kc mills. Brian, you work with him on that.
Yep.
And 3/0. And we're going to get no neutral in there so we can get that out of the case. Okay, and let's get the equipment grounding conductor out of there, because that really has nothing to do with that at all. Now, Brian, here's what's happening. Whatever the resistance of the conductor is, the I²R heat that's going to be built in that is going to be the exact same between the 2, except the 3 conductors have enough surface area to dissipate that heat away from them. Where when you start bundling more conductors, the conductors inside can't get the heat because they're bundled with other conductors, and that heat then just goes to the other ones. The total surface area to the mass. It's the same reason why a larger wire has a lower current carrying per circular mil than a smaller conductor.
Because it can't dissipate the heat
Because
as well.
it can dissipate the
Okay.
heat.
Now I understand.
Okay?
Yep.
All right, so we'll do a little better job in our graphics to explain that. And that's why when you parallel conductors in the same raceway, even though they're parallel, they're physically 6 conductors in that example, the heat is not able to dissipate.
Okay.
Neutral conductors, and we'll talk about this, Brian, we want to keep this graphic also, somehow we'll work it out. Neutral conductors are generally not current carrying, and clearly equipment grounding conductors not current carrying. So when we're talking about adjustments, we're talking about when a conductor is generating heat. So when you put neutral equipment grounding conductors, it kind of helps a little bit, because they're then taking up some of the heat until a certain point that they get the same temperature, then they're not able to benefit anything at all. So now, let's take a look at an example. Let's say we're running a PV and we have 8 circuit conductors in there, 3 source circuits coming out, going into this combiner. And actually, we actually have that. You have 8 conductors in here. Well, if we go to our table with 8 conductors, that says 70% is the adjustment factor. We're now using, let's say, 12-gauge wire. 12-gauge wire, going over to our code book, we found out that 12-gauge wire, all the way back here, 12-gauge wire at 90 degrees C is rated 30 amps, right, Ronnie?
Yes, sir.
So 30 amps right there. We had the temperature adjustment of 8 conductors, which is 70%. Because of the bundling effects, the heat not able to get out of that, we then take, the 30 amp wire times the adjustment 70, we have 21 amp wire. Of course, if we went back to our table, we realized the maximum overcurrent protection on 12-gauge wire is a 20 amp breaker anyhow. So if an inspector comes out and gives you all kinds of crap because you have the Romex all bundled and you can't explain to them that, listen, you don't have to use the lower ampacity for the entire circuit, you can simply adjust that whole circuit, take 8 conductors, up to 9 conductors, adjusted 70%, gives you 21 amperes, and you're fine anyhow. Okay? Now, we spent a lot more time in our calculations class on this. This is just briefly getting you an introduction. Now we can have the exception or the rule about the 24 inches. And that is, listen, if you do all these calculations and you're in a raceway that does not exceed 24 inches, well, because of the heat Brian, can get out at both ends. It's only that
Not worried
much.
about it.
And like, okay, well, don't worry about that because we can heat the heat sink can
Right,
get out of there.
right.
And that's why we can do that there. Now, raceways on rooftops. Raceways and cables exposed to sunlight on rooftops. There used to be a table, 310.15b3a, that specified that when you had a raceway on the rooftop, a distance above the rooftop, you would have to add additional temperature to the temperature that was expected to be at the ambient temperature of that roof. And what they did was they discovered that that whole data was flawed. It was all flawed. It was promoted by the Copper Development Association in conjunction with the IAEI in Las Vegas using a black roof using rigid metal conduit. And they were able to find out if you put rigid metal conduit on a black roof in Las Vegas, that pipe got really, really, really hot.
Okay.
So then they took that information, they required a code to require you then to sit there and basically the temperature correction factor would be like almost double the size wire. And of course, nobody in the United States that I'm aware of ever has found a raceway on a roof that's ever failed because of any kind of temperature problem. But we had to deal with this for the longest time, a couple, 3 code cycles. And what happened was, I don't know the story about this, but somebody did a study. And what they did was they put thermal couplings on the conductors, Eric, inside the raceway. The thermal couplings before were on the outside the raceway. And when they put the thermal couplings on the inside the raceway, they found out that when the raceway got hot, guess what it did? It started sucking air. It became then a coolant. And those conductors did not get hot. There was no problem. So they pulled the table out, but they left this in it. And it says, look, where raceways or cables are exposed to direct sunlight and located less than 7/8 from the roof, then you have to add 6 degrees Fahrenheit to the temperature if it's less. So what do? You put the pipe 1 inch above the ground, above the rooftop, and then we're all fine inside there. Not a problem there. Mike.
Now we've sealed the end of one end of that conduit, so we're not going to be moving air through it anymore.
I don't know that is the case, and how much that affects because I don't have the study. I'm just telling
Oh, I
you
know.
what I heard. I'm not saying that's exactly how it was.
Right.
But maybe that somebody from the copper development or here's what you just said, they're going to go take some more rigid conduit, put it on a black roof and rigid
Good job,
on
buddy.
Las Vegas, and they're going to seal both ends, and they're going to say, possibly inside there.
Pipe melted.
Okay. You know what?
Put the table back.
Basically, conductors outside, the effect has no effect on anything. Because, Eric, you use the higher ampacity, 90 degrees C. You use your temperature correction factor up to 104 degrees. And then that gives you back to an ampacity is what you would have used anyhow for the 75 degrees C. And then we're fine. So we went around in circles that we don't have to worry about any of this. Okay, neutral conductors. Now we're talking about current carrying conductors. Now understand this. If you have a 2-wire circuit, and let's put on there 4 wires in this box. If we had 4 wires, and maybe another example like this, well then the neutral conductor is carrying current, and the phase carrying current. Well then you have 4 current carrying conductors. But if you have a 3-wire neutral, 122 40-volt circuit, okay, the neutral carries the imbalance. It is not considered a current carrying conductor. If you have a 3-phase 4-wire Y circuit, the neutral conductor is not considered a current carrying. Mike, don't say not counted. It's just not a current carrying conductor. Yes, Eric.
Yeah, a lot of confusion about this because it says, well, wait a minute, the neutral carries current. You know what? What if I have line 2 and line 3 off and I'm just running line 1? Well, the neutral is carrying current. Okay, and so when we explain this to people, it's like, yeah, you're right. But here's the situation: you have 4 conductors going through a conduit. Now, if you have 10 amps, 10 amps, and 10 amps on the lines.
We're going to get that in a second. I'm just saying that, yes, you
Right.
could have a scenario that you have some neutral current, but even if, let's look at the language of the code, because sometimes I just want to make sure that people are really reading the language of the code
Right, and while you're looking that up, the long and the short of it is simply this. No matter how you add the currents, no matter how, you will never get more.
Wait. I want you to do that. I want you to do exactly that.
Okay.
I want people to be where you're at here. The neutral conductor that carries only the unbalanced current from all other conductors of the same circuit of the same circuit shall not be required to be counted when providing provisions. Now, I don't know what else the neutral conductor could be doing but to carry the unbalanced currents. You with me? So you add words and you're like, but what if it's not carrying that's, I don't know how to say this, but that's what it does. Okay, so you have a neutral wire is all it's saying, right? Because that's all it's saying. You have a neutral wire. You can only wire the code by one neutral, by one circuit, no matter what it is, however you want to do it, what? It's not a current carrying conductor. Now, you can explain it, though, because if you had a line 1 and a line 2 was a 15 and it was a 10, the neutral carries 5, Well, the power, though, is not going to change because it could have been, right, Eric?
Well, and another way of saying it is simply this. If the neutral is carrying anything whatsoever, then it means that some of the line conductors are carrying less.
Right.
And so it's never more than 3 conductors worth of current, never.
Now, watch this. This is true, and this is where there's confusion from past tribal experience. But Mike, I got a comment here from Dan in Philadelphia. I thought non-current carrying neutral conductors only applied to balanced services. And you know what? At one time in your lifetime, you were right, but you're not now. Because this number 5, 31015B5, said that the unbalanced conductors of balanced circuits. Well, then you say, well, 10, 10, 10, 0, right? Then it doesn't count. But somebody who's an engineer say, wait a minute, guys, simply the neutral conductor, no matter how you want to work out the math, it has the same amount of heat, it doesn't count. Okay? So back over here to this graphic here. I don't care what you do, your neutral conductor is not considered a current carrying conductor. Now, but there's an additional number 5B, and it says this. In a 3-wire circuit consisting of 2 phase conductors and the neutral conductor of a 4-wire 3-phase Y-connected system, a common conductor, not sure why they use the word common conductor, the neutral conductor carries approximately the same current as the line the neutral currents of the others. Why are you telling me that? Why don't you just tell me what the rule is? Well, we just want to just kind of show you that we know what we're talking about. Shall be counted when applying the provisions of 310.15b3a. So, Eric, this graphic, talk to me about this one.
100 plus 100 equals 100.
In other words, if you run 2 hots,
Right.
and that wasn't what I was looking for, but I'm going to go with what I got. You know what I mean? So if you look at this graphic here, if you have 3 wires off of a 4-wire system, then the neutral conductor will carry approximately, well, the neutral conductor is going to carry current, and it's going to be a function of this square root of line 1 squared plus line 2 squared minus line 1, line 2, and the example shows you how it comes out to be 100 amps.
And where you have to watch this is when you have a 3-phase transformer feeding, for example, construction trailers. Because the construction trailers are 2 phases and a neutral. And so in that case, you have 3 current carrying conductors in the raceway.
Which wouldn't matter because we have 3 current carrying conductors.
Right.
Unless somehow I was paralleling. Now the neutral conductor of that single phase would be considered a current carrying conductor.
Right.
David.
Well, a 3-phase service feeding a multifamily building, and each multifamily unit, each dwelling unit is only being fed with single phase 208.
And that means those are 3 current carrying conductors, which
That's
still
right.
complies with table 310.15b16, and we're still okay. So there aren't many cases where you'd be running 3-wire circuits of a 4-wire system where you'd have to be putting multiple circuits in the same raceway, but we then count the neutral conductor. So in reality, it's a pretty limited application, but it's true. So back over here. Now we have number C. And C tells us this. Nah, that's your 2-wire circuits. Let me see if I want to have it. All right. Let me just make a statement, then we'll look at the code. Odd triplet harmonic currents from nonlinear loads add on neutral. Okay, we don't have a graphic that really covers the rule, so we need to get a graphic that covers the rule. Here's the rule. On a 4-wire, 3-phase Y circuit, where the major portion of load consists of nonlinear loads, harmonic currents are present in the neutral conductor. The neutral conductor shall therefore be considered a current-carrying conductor. I find this fascinating that this rule is again teaching us. It's trying to tell us why. You don't have to tell me why. You can just simply say, hey, you got a 4-wire circuit, 3-phase, and your major portion supply nonlinear loads. It's a current-carrying conductor. Drop it. But they said, oh, you know, we learned the word harmonics. We want to use it. We want to tell you what we learned. Okay, is that a bad thing? Harmonic currents are present in the neutral conductor care for da-da-da-da. So if we look at the graphic here, let's see if I know the graphic. I pulled the graphic out. In other words, theoretically, you could have 100 amps on line 1, 100 amps on line 2, 100 amps on line 3, and what should have happened is that we should have had no current at all on the neutral conductor. But because you had nonlinear loads, and we need to work on this slide here, you have what is known as odd triplet harmonic currents. And those odd triplet harmonic currents are going to be additive. And they could theoretically add up to 300 amps. I mean, that would be, of course, it's not possible, but I mean, that's the theoretical thing, that you have 100% harmonic distortion. I'm not going to get too far. You'd have 100, 100, 100. This happened back in 1988. An article was written by a guy named Art Friend, and it said double the neutral or else. And that's the first time it happened in Chicago. There was a union electrician in Chicago. He put an amp meter on line 1, put an amp meter on line 2, put an amp meter on line 3, and put an amp meter in the neutral. And the neutral current was like double the current of the phase conductor, and he didn't know what happened. It started this whole industry to find out electronic ballasts, electronic loads were coming in, and those loads did not have filters to capture the harmonics that was being generated back into the system. What simple little example of harmonics is, you got water flowing in a pipe, and then you slam it closed just like that. What happens to the water? It hits it, and it does what? It bounces back. Yep. And that's what's happening in electrical systems. And of course, these are the electronic power supplies. They're what? They're off. They turn on real quick, called switching power supplies. So as they switch on and off, as they switch, they're just creating all this reflective currents going all back, and it goes on the neutral, then it becomes added to the neutral, and then we had to size the neutral, double the neutral size, and then we had to get panel boards. Well, the problem with the panel boards, panel board neutral buses, just so you know, if you had a 200 amp panel, the neutral bus was sized at 70%. Years and years and years ago, there was a 70% number that we used in the electrical trade for the neutral load. Okay, so then that 70% came into the sizing of the neutral bus. Then when we had the problem with the harmonics, when the neutral bus is actually burning up because they took these existing installations, had to be 3-phase, 4-wire, 120, 208, 277, 480 in schools, and now having all these computers going, then all of a sudden they changed the light fixtures, the electronic ballasts, and all kinds of things are developing in there. They're burning up the neutral in the buses. Yep. So what they then did is they then came out with, I think it's an LP panel. I don't know if it's still around anymore. They come with K-factor rated transformers because the transformers are heating up, because the transformers were not designed to be taking this kind of heat. The neutral bus was not there. We doubled the neutral, and today's neutral buses are sized at 100%. But you can get a double. But there are still people out there, I'm sure, that's specifying a double neutral that wants to have a special sized panel, but the manufacturers now of the electronic equipment, the computers, the switching power supplies, the electronic devices, they have filters. It's kind of like a surge protection in reverse. In other words, it just captures those, and they're tuned to the frequency that's going to be reflective of the power supply. And so that's where we're at now. So now let's go back to the code. On a 4-wire, 3-phase Y system where the major portion of the load consists of nonlinear. Now, what's nonlinear loads? Copy machines, printers, scanners, fluorescent lighting, LED lighting, computers, our personal
switch power
computers,
supplies on the
anything
computer.
that's not operating linear. Okay. Pretty easy. So if we know what a linear load is, then we know what a nonlinear load is. What is a linear load? That means that the voltage and the current are, I'm sorry, take that back. A linear load means that the load, the impedance of the load is linear. It is constant. An incandescent light bulb. It has a constant impedance. It doesn't change. So therefore, it is a little baseboard heater that you plug into a receptacle. That heat is on. That resistor is there. That is a linear load. It's when you have
loads.
switching power supplies that are doing all kinds of things where the voltage comes in at 120, but the frequency is different, the voltage is different. You know, you're doing different things inside there. Well, then whatever that is, that's linear. So many of our loads are going to be linear. As a matter of fact, probably in an office building, I'm guessing the air conditioning, right, is not linear. The heating is not linear. The water heater is not linear.
The water heater is linear.
I'm sorry. The water heater, let me phrase that. The air conditioner is linear. The water heater is linear. These are big loads, right?
Yeah.
Because you got to realize it has to be the major portion of the load. Now, but watch this. Let's assume I have a 400 amp service and I have 200 amps of line to line loads. You with me? I get that out of the way. That means I have 200 amps of linear loads. I'm sorry, 200 amps of line to neutral loads. A major portion of that 200 amps has to be nonlinear. Not a major portion of the service, major portion of the neutral. So therefore the neutral is considered current carrying. Brian.
In most instances, it's going to be because almost all modern lighting is going to be nonlinear loads, whether it's fluorescents, LEDs, HID. It's just there's going to be so many different things that are nonlinear loads. So, yeah, I mean, that's just a way of life now.
So what we can do is distill this down. I like to distill it down to nothing, okay? All right, you have an office building?
Yeah.
The neutral is a current carrying conductor.
LEDs are.
Sure, they don't
Yeah.
operate at 120 volts. It isn't like you put 120 volts to a light bulb. You have a power supply.
Switching power supplies, yeah.
As soon as you're changing voltages, you with me, Dave? I can't think of any light. Okay, the only thing that would be not linear would be an incandescent light bulb, a halogen light bulb, right? Because it works off of the voltage. Everything else,
Any resistive heaters.
Space heaters.
space heater,
Yeah,
any
the
resisting.
resistive loads.
Right.
But you mentioned a motor load also.
A motor is not. A motor is a linear load.
Inductive, right?
It's a linear load.
Okay.
We're not changing voltages. But variable speed motor drives.
Yep.
Well, that's a linear load. Well, it's not a motor. It's a variable speed
The
driver.
VSR, right.
So anytime you're changing something,
That's a nonlinear load.
that's a.
VFD.
You said it was a
Yeah, I'm
linear
sorry. It's a
load.
nonlinear load.
Correct.
Right.
Frequency
Because it's a power supply. Right. You take 120 volts. You go right to the motor.
Right,
That is a linear load.
okay.
So in office buildings, can we be comfortable to say the neutral loads, line to neutral loads, those are going to be linear, they're going to be non-linear loads, and so therefore that neutral conductor will be considered a current carrying conductor.
I'm surprised that,
We can take it further than that.
No, let's not go there yet.
Okay.
I'll tell you why. Once we can establish that, that means that in all our calculations and everything that we do in our graphics, we would have to calculate out to make sure we size the conductor at 110.14C1B about the 75 degree C. But we'd have to also verify 310.15B3A that there's 4 current carrying conductors in there. And Eric, we're going to use the 90 degree C adjustment ampacity at 80% to verify that the conductor we're going to use. And then Brian, we can't forget 240.4B,
Right.
that we have to protect the conductor at its ampacity in coordination with 240.6.
I wasn't even going to go
No,
that deep.
I want to just finish
Okay,
that up.
okay.
In other words, it's a nonlinear load where it's a neutral,
Yep.
it's current carrying. We got to make sure we figure out the ampacity adjustment to make sure the wire that we size at 75 degrees C can be used after the adjustment factor is made. Okay, are we okay with that concept?
Yeah.
Okay, now Brian, I just want to
Yeah,
make
no,
sure
it's
we don't
okay.
switch yet.
I just wanted to maybe make it even simpler. In modern society, if you have a line to neutral load of a service, it's going to be very rare that there's not a current carrying neutral if it's three-phase.
If
Why?
it's three-phase,
three-phase.
office buildings.
Well, no, could be three-phase apartment complex because you got LED lighting, you've got fluorescent lighting, you've got.
I don't think residential.
Why is that?
I don't think 50% of the neutral load in a dwelling unit.
Other than air conditioning,
No,
which now has.
you have all the 120 volt appliances. Dishwasher.
I think we'll have to find out.
You'd have to do
I'll
a
find out.
calculation.
Yeah,
though.
I'm going to do
Well,
it.
we're going to do that when we do calculations next
Perfect.
month,
Yep.
or the month after that. We're going to calculate and find out when does a neutral conductor become current carrying.
Yep.
But I agree with you. It has to be three-phase. By the way, this nonlinear load, if you take a look at this rule here, it says on a 4-wire three-phase Y. So this does not apply to single phase. It's only
Right.
4-wire three-phase. That's where the graphic is talking about the odd trip and harmonic currents. Okay, so let's move on. Single phase dwellings, services, and feeders. Okay. Service and feeder conductors for a one-family dwelling supplied by 120 volt can be sized. This should not be anything, no voltage. It just should be, forget about the voltage, Mike. Can be sized not less than 83% of the service rating. So we don't need a voltage in there. He says this. All you got to do is calculate your service disconnect, take 83% of that. That is the size of your service conductors, and that is the size of your feeders. The voltage is irrelevant. Period. One family dwelling. Now, here's an example. If you did a calculation, you had a 200 amp service disconnect, well then 83% of that value is the ampacity of the conductor requirement. Then we'd look at the table, what's 166 amps, we would use 2-aught rated 175. Now there used to be a table in the code book that just simply said 200 amps, here's the wire size. I'm not going to get into the whole history of why they did that because it's just no need to bring up bad feelings, okay? We got to go with the 83% calculation. Or if you want to, go to the old code book that had those tables, make a copy of that and stick it in your code book now. Then you don't have to do the 83% and then go to the table to find out what's the wire that's required to get to 83%. 1 and 2 family dwellings, services and feeders. Let's go to 2 family dwellings. It should say here, yes, service and feeder conductors. Forgetting about the voltage, can be sized not less than 83% of the service rating. I don't know if we have an example or not. No, we don't. But if we had an example, and if this was a 200 amp, we'll do another graphic with a 200 amp. Well, if it's 200 amp, then you're basically back over here. We use the same thing, just show 2 meters disconnects on both sides. You're going to run 83% of 200 amps. That's going to give you 166. It doesn't matter what the voltage is. If you're running a conductor to a dwelling unit, and we have to make sure we add a little bit more text in these, where it's carrying the entire load supplied by the service. So we need to make sure we get that in all those graphics. So back over here in a one-family dwelling. On a one-family dwelling, if the service conductors and the feeder conductors are carrying the entire load supplied by the service, then I can go 83% and go that way. In a duplex, if the service conductors here and the feeder conductors here are carrying the entire load supplied by that service or feeder conductor, then I can go 83%, and then I can go with that calculation. I cannot use the 83% rule for a 2-family dwelling at this location here, because it's only permitted, let's go put the language here, for individual dwelling units. That the key word there is the word individual dwelling units, and this service conductor right here is not to an individual. But these service conductors are to individuals. These feeder conductors are to individuals. And if it carries the entire load by the service, I can use 83% here, but I cannot use it there. Let's go. Yes, Dave.
I've seen some confusion once in a while where on a single family dwelling where they would have 2 main breaker panels fed from the 1 meter.
You know
and
what?
Trying to use that table.
I really like what you said. So right over here after this graphic, we need to show a graphic with 2 main breaker panels from 1 meter. And then we have to show how you cannot use the 83% rule if you go with 2 main breaker panels.
And the same thing with like a 400 amp meter main with 2 200 amp mains in it to feed 2 main.
And that would be a good example where you have a 400 amp meter main. 400 amp meter main?
400 amp meter main with 2.
Do they make 400 amp meter mains?
Yeah, with 2 200s, and then even a sub panel off in it as well.
Okay, well if you have a 400 amp meter main,
Well,
You could use it for the service,
for the 400 amps
for the
coming
400
in,
amps, because it's to an individual
but it's
dwelling
all
unit.
one box.
But you can't use it for the individual 200 amp feeders because they do not carry the entire load supplied by the service. Very good examples, David. Excellent. So now let's go back over to a meter stack. We want to get rid of the voltages here. Feeder conductors for individual dwelling units can be sized using the 83%. That's individual dwelling units of a multifamily dwelling. And you notice I keep saying remove the voltage spike, remove the voltage spike, remove the voltage spike. Because what they did was this in the 2017 code. And you can see what my logic is. I always try to keep things as simple as possible. Here it is right here. Where's the, okay, here we go. Here's the basic rule. The first rule says you can do this for 120, 240 volt systems, the 83%. That's 1 through 7. And it says you can do it for 208Y 120 volt systems. Well, you can do it for a raceway underground or above ground. Or you can use it for a plastic raceway or a metal raceway. Or you can use it for 120, 208 or 120, 240. Well, there are no other voltages for dwelling units. Now, here's the history to understand what's going on. It makes sense to do this, but I want you to understand where it will propose to get rid of it. You got to realize, to my entire career, this permission to allow you to have a smaller conductor based upon the calculated load was always based upon a 120, 240 volt single phase system. And it specifically said you could not use it for a 120, 208. Eric, the reason they said you could not use a 120, 208 is because the neutral conductor was considered a current carrying conductor, but three-phase, four-wire system using 3 conductors. And they said we don't want to use it there because that neutral conductor is current carrying. Now, how that thing got switched around after 125 years, I'm not quite sure what it is. But they went ahead and they allowed us now to apply to 120, 208 as well as 120, 240. If that being the case, I can get rid of, watch, dwelling units. It can be used. I don't care what the voltage is for a one-family dwelling. A duplex. I don't care what the voltage is because it can be used for 1 or 2 family dwelling. Multifamily. I don't care what the voltage is. But watch what they made a change. What they said. They said, look, if it's 120, 240, you can go 7.1 to 7.4, right? But if it's 120, 208, they said 7.1 to 7.3. Like, oh, wait a minute now. We got different conditions here. Like, okay, well, we got to keep them separate. But then let's go to 7.3 because it doesn't apply to a Y system. I mean, 7.4 doesn't apply to a Y system. You ready for this? Grounded conductors, which are what? What do they call? What do we call them in our class? Neutral conductors shall be permitted to be sized smaller than the ungrounded conductors. Now, this class is not part of the scope, but when I get in my calculations class, we go to 22061, and you size a neutral based upon the calculated load. It's not a matter of being smaller, it's a matter of being sized. You usually have less loads lying in the neutral than you have the total of the service, so the neutral would be smaller simply because it's a less load on the neutral loads. Okay, neutral conductors shall be permitted to be smaller than the hot conductors, ungrounded conductors, if the requirements are 22061 and 642 for certain order are met. What do you mean if? I have to comply with that. I mean, if I comply with that, I can size the neutral basically to the calculated load. Hold on. Up here in the beginning, on a 120/240, I can size the conductors B7 1 through 4. Okay. Now, if I go over to 120/208, it says 1 through 3. Oh, I see what they did.
Yeah, because
So what they're saying is that, yeah, we'll let you go to Y system, but what do you have to do with a neutral conductor?
it's current carrying. It's totally current.
You have to have the neutral conductor the same size.
fully sized.
Full size.
No reduction of neutral.
No reduction neutral conductor. In other words, you can't size the neutral conductor, not a reduction. You
Right.
have to make the neutral conductor larger,
Right.
right? You can't size it per the code. You have to make it larger. Why? Because, Eric, that 120/208 three-phase, four-wire Y is single phase, that extra heat, we're going to solve that problem by allowing you to have a bigger neutral, bigger than what's required by the code. You go with a full-size neutral, you're allowed to do that. Most people probably put a full-size neutral. So, Brian, we have to just be very careful in our graphics. Let's look at our graphic, guys. Let's see if this is true. Regardless of the voltage, I can size 83% to a dwelling unit service and feeder. True or false? Regardless of the voltage, to an individual dwelling unit, a one-family dwelling, I can use 83% service and feeder.
True.
Yes.
The entire load supplied by that,
Okay,
right?
okay.
I mean, that's what the rule is.
Well, yeah.
And there's the example. If it's a duplex, regardless of the voltage on a duplex, it doesn't matter. I can size the feeder conductors 83%. Right?
Right, right.
Multifamily, regardless of the voltage, I can size the feeder conductors 83%. But in this case here only, if it's a 122.8Y, the neutral has to be what? Full size. So the feeder conductors are all fine. But if you want to go to a 122.8Y single phase of a three-phase 4-wire Y system, then the 122.08, we need two graphics here. One is 122.40, 83%. The next graphic is 122.08, 83%, but the neutral is sized at 83% as well. Eric?
You know, the way of looking at with a 12240 volt system, if we say we have a 50 amp line to line load, then we say, okay, that's 50 amps line to line. There's nothing on the neutral. But if you do the same thing on 12208 and you have a 50 amp line to line load, you still have 50 amps on the neutral.
Right. Right. Okay. And now, here's an interesting one. The feeder isn't supplying the entire load. So right here, see this feeder right here? Because you can clearly see the service, is it supplying the entire load? Mm-hmm. Yes. Is this service conductor supplying the entire load? Yep. Yes, right? So therefore, I can go 83% here, 83% here. But this feeder right here does not supply the entire load supplied by the service. So therefore, 31015B72 can't be used to size the feeder conductors, except as permitted in 31015B73. Now look at that one. In no case shall a feeder for an individual dwelling unit be required to have an ampacity greater than specified in number 1 or number 2. In other words, let's just assume the 83% rule here came out to be 160 something amps, right? And it was, I don't know, whatever that wire was, 1 aught. Let's assume over here the calculated load, the way it worked out, because you can't go 83%, you have to now put 2 aught. You with me? Well, they're saying, no. If you only need to have 1 aught coming in here, there's never a case where the feeder that's not carrying the entire load supplied by the service having to be larger than the conductors coming in. So when we have the service and you have 2 different panels, you have a meter main, you know, you have a panel with feed-through lugs.
Yep.
Right? You got a panel with feed-through lugs, and you pick up a couple breakers out. Say, oh, you're not supplying the entire load by the service, so it's not going inside there. You can't take 83%. You can 83% coming in here, but not inside there. So now you got 1 aught coming in here, or you got whatever it is, and then you got 2 aughts going in there, but the feeder conductors never have to be larger than the service conductors coming in the feeder in the first place. So that kind of makes sense there. Brian, anybody?
I was just going to say this. Actually, a common application of this is 200 amp meter main combos. That's actually where this is really handy. Going into the house, you don't have to be bigger than the wire that's coming down the riser.
There you go. That's it. I like the way you phrase it there. No conductor has to be larger than the conductors going down the riser.
Right.
No matter how you, whatever you do, you calculate. Size your wire, guess what? Another simple way. What size wire do we need to the riser? Okay, that's the largest wire we have to have from that point forward, right? It never has to be larger than that.